Hello, today we're continuing in our A-level physics revision series looking at the subject of X-rays. X-rays are produced by the use of the principle of the cathode ray tube, although in this case of course it's called the X-ray tube. Basically you have a tube, I won't complete it just yet for reasons you'll see later, and you have a cathode and you have an anode. But in the case of an X-ray tube, the cathode and the anode have a voltage of the order of 20 to 100,000 volts. So 20 to 100 kilovolts across this tube. The tube is completely evacuated, and as you might expect, cathode rays, which are of course electrons, will flow from the cathode towards the anode. So far, so good. Now the anode is typically made out of a substance called tungsten and is shaped in this way so that what happens is the cathode rays, or the electrons, hit the tungsten, and emerging from the tungsten come X-rays. And that's why I left the gap there. There's a little window here through which the X-rays pass. The cathode will typically have a separate circuit which heats the cathode in order to drive the electrons out of the cathode, and they are then attracted of course to the positively charged anode. Now the question is of course, why do electrons, cathode rays, coming across and hitting a tungsten anode cause X-rays to flow out? And there are two processes by which X-rays are produced. The first is that if you take this as a tungsten nucleus, it will have 74 protons in each nucleus. So it's quite a high charge. And if you've got a cathode ray or an electron coming past that nucleus, then the chances are it's going to, by electrostatic attraction, be, as it were, diverted as it goes around. Depending on how close it gets, it might be diverted quite a lot. Sometimes it may not be diverted by very much. But the point is, it will actually change direction. And a change of direction is acceleration. And when a charged particle, in this case an electron, is accelerated by changing direction, all charged particles accelerating emit electromagnetic radiation. And in this case, the electromagnetic radiation is emitted as X-rays. And if you were to plot the intensity of X-rays, that's the intensity, against the wavelength of those X-rays, remember wavelength is increasing, which of course means that frequency is decreasing, then you get a graph that looks something like this. So that there is essentially a cutoff where there are no X-rays that have a shorter wavelength than this, or a larger frequency than this. This continuous distribution of X-rays is called Bremsstrahlung radiation, which literally means, translated, braking radiation, because essentially the electron is braking as it passes the tungsten nucleus. Why is there an upper limit, or as it were a lower limit for the wavelength, an upper limit for the frequency? Well, the answer is that of course as the electron loses energy, it gives some of that energy to the X-rays that are emerging. And we know that the energy of a photon, and the X-rays will be made up of photons, is given by h nu, where h is Planck's constant and nu is the frequency of the radiation. So the energy that is derived from the electron is converted into X-rays at a frequency nu. Now the electron will have a maximum energy. That energy will be given by this voltage here. So the electrons that are coming across here will have energies of between 20 and 100 killer electron volts, keV. And that energy, or some of that energy, as the electron slows down, is going to be given up into X-rays. Now there's a limit. The electron can't give up more energy than it already has. So even if the electron gives up all of its energy, the X-ray will have a maximum energy corresponding to the energy of the electron. And that's why there's a cutoff. This represents the point at which there is no more energy for the electron to give up, and therefore the X-ray energy, which is of course h nu, has a maximum at that point. So Bremsstrahlung radiation, the continuous distribution of radiation according to wavelength, Bremsstrahlung radiation is the first mechanism by which X-rays are produced, but you will typically find that on this distribution you will also find peaks of X-rays. Where do they come from? Well, an atom of tungsten, which is the target, the anode for the cathode ray tube, will have 74 protons in its nucleus, and of course it will have orbiting electrons, 74 of them, in different shells. And what happens is that an electron that comes in from the cathode will be travelling very fast, very high energy, and what it can do is it can hit an electron in an inner orbit. So it comes in to that inner orbit and the two electrons fly off. It's a bit like one billiard ball hitting another billiard ball and they both go flying off. And so there is then a gap in the electron shell, in an inner shell. And what happens then is that an electron in an outer shell falls down into the inner shell to take its place. But when an electron falls down the energy level, it gives up energy. And of course it gives up that energy as a photon. And that photon is an X-ray. But that energy difference is well defined. And that means that the energy that the X-ray will get is well defined. And since energy equals h nu, where nu is the frequency of that X-ray will be well defined, and the frequency is one of these peaks. Obviously, electrons can come from several outer shells to fill an inner shell, and depending on which shell they come from determines the energy difference between the two shells, and that determines the specific frequency peak that you see, as it were, added onto this Bremsstrahlung radiation. Now it just so happens that only about 1% of the energy of the electrons that hit this target is converted into X-rays. The other 99% heats up, or is converted into heat, which heats up the anode. Consequently, that anode would get very, very hot. The energy of these electrons is very high. So what you tend to find is that the anode is shaped as a circular disc, and it's constantly spins, so it's spinning kind of on this axis. The electrons are hitting the slanted part of the anode there, but because it's spinning, not one single point is being constantly heated, and quite often there's a means of getting that heat to move away. If you simply had an anode like this, it would probably melt. But if you spin it around an axis, so that this is constantly changing, then there's a way of keeping it cool. Now the energy of the X-rays that emerge will depend on the frequency. This graph shows increasing wavelength in this direction, increasing frequency in this direction. So at this end of the chart, you have the high energy X-rays, and at this end of the chart, you have low energy X-rays. Why? Because at this end of the chart, you've got high wavelength, which is low frequency, and low frequency means low energy. And at this end of the chart, you've got low wavelength, high frequency, and high frequency is high energy. So high energy here, low energy here. What's the significance of that? Well, we want the X-rays to pass through a body and hit a photographic film underneath. Typically what you have is the X-ray tube here, a person sitting or laying on a bed, and a photographic plate is here. So the X-rays come down and penetrate the body, but to different extent, maybe not at all. If it hits bone, it will be attenuated or reduced if it hits flesh, and so you get an image on the photographic plate. But you want the X-rays to get right the way through and hit the plate. If they don't get through, but they instead get stuck in the body, they are part of the overall dose, and X-rays are dangerous, so you don't want to give patients more X-rays than you absolutely have to. So if you've got X-rays that are going to get stuck and don't penetrate the body, they're no use at all because they don't get to the photographic plate, and yet they count as far as the total dose is concerned. So you don't want low energy X-rays, which is the X-rays at this end. And so typically the way that you get rid of those is you put an aluminium plate across the exit of the X-rays, and that aluminium plate will take out all the low energy X-rays that would never penetrate the body, so that you've only now got the, as it were, high end of the X-ray spectrum, and that has got the energy to penetrate and hit the photographic plate. There is a further option here. You can increase the voltage. If you increase the voltage, that means you will increase the energy of the electrons which are hitting the tungsten anode, and consequently you will have higher energy X-rays coming out. In other words, this cutoff point will go off to a higher energy, in other words a lower wavelength, higher frequency, higher energy cutoff point. So if you want higher energy X-rays, you have to increase the voltage. On the other hand, if you increase the temperature of the cathode, you will produce more electrons, more thermal electrons, and that means you get a higher current, since current is flow of electrons. So you get more electrons coming across here, and that means you get more X-rays. So it's a question of varying the voltage in order to get higher energy X-rays, and the current in order to heat up the cathode in order to generate more electrons, in order to get more X-rays, that is a higher intensity of X-rays. So you get more X-rays by getting the current, by heating up the cathode, and you get higher energy X-rays by having a higher voltage. Now if you look at an X-ray, you'll typically see that it is fuzzy at the edges. And the reason for that is this, that if you take, here is the anode, which is emitting X-rays. Here is, say, the bone that you're maybe investigating. Then X-rays can emerge from anywhere on this anode. So, for example, an X-ray might come from the top of the anode and go just past the bone like that, or from the same position and go past the bone like that. Or an X-ray can come from the bottom of the anode, go past like that, or from the bottom of the anode and go past like that. And here is the photographic plate. Let's just extend those like that. And what happens? This part of the photographic plate is completely dark, because that's no X-rays can penetrate the bone. But here, some X-rays can and some X-rays can't. And so you've got a kind of a grey or fuzzy, it looks as though it's unfocused part of the position here. And the larger amount of, as it were, grey or penumbra is the technical term, I think, the larger amount of grey you've got here, the more fuzzy the picture looks. So what's the solution? Well, the solution is to make sure that the X-rays emerge from only a small part of the anode, let's say there, and here's the bone again, and now you will see that the where are we going? Not very well drawn, they should have been straight lines, but you'll see that the grey areas are now very, very much smaller. But you've got to have a certain defined area of the anode to emit the X-rays. You can't have a pinpoint, it has to be a finite area, and that finite area will mean that there will always be a small amount of grey on either side of the image on the photographic plate of the bone. And that's why when you look at X-rays, they always look as though they're a little bit fuzzy. And the way to sharpen the image as best you can is to have the X-rays emerging from as small an area of the anode as possible. There's a further problem. Let's say that you've got an X-ray tube sending out X-rays like this, and you've got some part of the body here, and you've got a photographic plate here. What you want is for those X-rays to go through, straight through and out the other side and hit the photographic plate, and they will be attenuated, that is to say their intensity will be reduced as they go through this part of the body, depending on how thick that part of the body is, how much it will attenuate the X-rays. What you certainly do not want is for an X-ray to be deflected by hitting something and coming off up here, because then that will give a completely wrong picture on the plate. And the way that you solve that problem is you put lead gratings, so that X-rays which come straight along will go through, but X-rays that have been diverted will effectively be stopped by the grating. And so only X-rays which pass straight through the piece of tissue in the body and then through the grating will hit the photographic plate. All X-rays that have been deflected will just simply hit this piece of lead and be absorbed. The lead grid, of course, typically will have to be quite wide to ensure that only X-rays which are travelling in this, as it were, parallel from the X-ray tube pass through and hit the screen. Any X-ray which is travelling at an angle as a result of having been reflected will be absorbed by the lead grid. Hello, today we're continuing in our A-level physics revision series looking at the subject of X-rays. X-rays are produced by the use of the principle of the cathode ray tube, although in this case, of course, it's called the X-ray tube. Basically, you have a tube. I won't complete it just yet for reasons you'll see later. And you have a cathode and you have an anode. But in the case of an X-ray tube, they're made out of a substance called tungsten and is shaped in this way so that what happens is the cathode rays, or the electrons, hit the tungsten, and emerging from the tungsten come X-rays. And that's why I left the gap there. There's a little window here through which the X-rays pass. The cathode will typically have a separate circuit which heats the cathode in order to drive the electron in each nucleus. So it's quite a high charge. And if you've got a cathode ray or an electron coming past that nucleus, then the chances are it's going to, by electrostatic attraction, be, as it were, diverted as it goes around. Depending on how close it gets, it might be diverted quite a lot. Sometimes it may not be diverted by very much. But the point is, it will actually change direction. And a change of direction is acceleration. And the cathode and the anode have a voltage of the order of 20 to 100,000 volts. So 20 to 100 kilovolts across this tube. The tube is completely evacuated, and as you might expect, cathode rays, which are of course electrons, will flow from the cathode towards the anode. So far, so good. Now the anode is typically electrons out of the cathode, and they are then attracted of course to the positively charged anode. Now the question is of course, why do electrons, cathode rays, coming across and hitting a tungsten anode cause X-rays to flow out? And there are two processes by which X-rays are produced. The first is that if you take this as a tungsten nucleus, it will have 74 protons